Okay, welcome to lecture, and thank you for allowing me to set up my computer while I'm figuring all this stuff out. Now, let's see here. I have now all of the chats open on this side screen TV so that as I'm lecturing, if you have questions, I should be able to see them. I also see them on this monitor here, but that way everyone can see what the rest of the class is asking. And I'll be able to put my PowerPoint slides on the projector here, but also everyone should be able to see them inside of my portal here as well. So let me pivot this. Now let me ask you this. Am I in frame with the camera since I turned the video panel off? I guess I can turn it on here too, so that I can actually see, so that I don't fall out of frame when you watch the recording, because there's nothing worse than seeing half of a head in the thumbnail. Perfect. Okay, if I fall out of frame, just let me know, because I can't see anything on my end, and I know it's taking from my laptop. Okay, so yeah, the first homework I want to say is due on Friday in Moodle, but it's really designed to be not so much a homework that illustrates that you know how to do any Java. It's a homework that illustrates that you're prepared to start doing Java. So it's super critical that by the first week, everyone has a developer environment, so that on a machine, any machine, you can create new Java files, implement those Java files, and execute those Java files so that you can compile your source code into bytecode and then take your bytecode and actually execute it. And so you should be doing that in lab this week. And so there's one of two ways that you can get your machine set up. You can either do it on your local machine, your Windows, your Mac, or if you're running a Chromebook, you can't necessarily do that, but you can still get a developer environment set up without having to do any installation. That's the second way. You can just access the web terminal that we host the thin clients on. So if you look at all the computers in our computer lab here, they aren't actual computational computers. They're thin clients that connect to our data center that we have on the third floor. If you haven't seen the data center on the third floor, if you haven't been on the third floor yet, I'd advocate everyone take a field trip up there at some point, because that's the domain of computer science. That's where our entire department resides at. And you as students, as computer science students, are all welcome to go up there. There's like a study room up there. That's where the help desk will be at. There's some computer labs that will be available if they're not being used for classes. So keep in mind, you have a space on campus upstairs that allows you to work without having to go to the library or the UC or any other kind of public place on campus. So yeah, with that said, you can make the trip around, because it's in the math building. The math building is built like a circle, right? So you can make the trip around. You can see the data center behind, because it's got glassed doors of sorts, or at least a glassed window. The rest of the doors would, but that's also where all of the offices are going to be at. So you can kind of see who's going to teach the rest of the classes. And that's where my office would be at as well. That's where the I'm sure everyone's actually been up there at least once, or have you just corresponded through email mostly? I don't know. It's weird in this this post-COVID world, because you can do so much now without actually seeing other people. But that's where the main office would normally be at as well. So if you were doing advising, or if you had to talk to your undergraduate coordinator, or if you're trying to get into the master's program, you're taking all the base classes, that's where the graduate coordinator would be located at. Although I think Dr. Stima's office is now in the hallway. Excellent. So is there any questions regarding that? What is the building called? Math. It's the mathematics building. Excellent. So what I want to do today then is I want to move on and start actually with our lectures, actually start discussing what is going to take to build you, to forge you into software developers. And so I'm going to slowly translate the notes that I had, the GitLab notes that I had posted a couple of years ago, into PowerPoint slides, because it's easier for everyone to see what I'm talking about. So we'll have some very ugly PowerPoint slides, but they're just prompts for me to be able to talk and show code and whatnot. So let's start with Unit 1. So when we looked at the syllabus not too long ago, we had discretized the course into 3 units. right? The first unit is algorithmic thinking. The second unit will be drive principles, and the third unit will be object-oriented principles. So let's motivate this concept for unit 1, which is going to be algorithmic thinking. So before we even get into how we can think algorithmically, let's motivate why you're even in this classroom today. Why study computer science, right? Well, let me give you some reasons why it's worth the effort to go through this program. We are a digital-driven society, right? What does that mean? Well, that means that up until very recently, like within a lifetime, we not only exist inside of a physical world, but we've been building this cyber world that we use to perform our occupations, right? It aids every profession, and it aids every individual who is a member of our society. Like, think about it. Everyone around us. I'll do a quick survey. Like, in this room, how many people use software? Yeah, like every day, right? Especially during the COVID years, right? That's how you interacted. So you use it for recreation, you use it for communication, and you use it professionally. Okay, so let me ask you this. That's what it means I say we're a digitally driven society, right? It's where we make use of this in our day-to-day life, in every aspect of our life. There's no getting away from it. And in fact, we're only embracing more and more use of software in our daily life. I wager to say this. So everyone uses software. Let me remove that by one step. Let me go one step further and ask, is there anyone you know who doesn't use software? No, right? So think about the pool of people we're bringing in here. It's not only everyone in this room uses software, but everyone in this room, and then everyone that they know also uses software. And you'd be really hard pressed to find an individual at this point that doesn't use software. So we're talking about how every individual person uses software, every job. Can you think of a single job that doesn't use software anymore? Like, regardless of what you end up becoming. So you're in a computer science class now, but like biologists use software, right? Like chemists use software, mathematicians use software, physicists use software, right? Doctors use software, teachers use software, business managers use software, accountants use software, right? Writers use software. Okay, so this is the next question. So we've certainly asserted that software is heavily used in everything. Let's start looking at this temporally now. Would it be fair to say that currently your current version of yourself uses more software on a daily basis than you did 5 years ago? Yeah, it's true for everyone, right? So is it so much to forecast? And well, before I forecast, let's do that example one more time. 5 years ago, would you have wagered to say that you were using more software back then than you did 10 years ago? Okay, so 2 data points there. So now let's forecast. Is it safe to assume that 5 years from now, you'll likely be using more software than you're using today? So we've established a world, a reality, where software is in the fabric of our society. Everyone relies on it. Everyone depends on it. More and more people are using more and more of it. And that pace, that behavior doesn't seem to change. And so this is where it gets really interesting. You see something that is so fundamentally important to how we all live and work now. And then the next question is, how many people know how to make software in our society? And I did a survey of that not too long ago, right? I did that last lecture. I asked how many people here know how to make software. And I want to say it was about 1/3 of the class, right? That's really good. That's more than what the norm is if you were to take a poll on society at large. So think of the career opportunities you have. Why the job market is so good for software developers. It's because it's literally something that within a generation has become a requirement for living in the society. It's what we use to facilitate everything we do, whether it's for fun, whether it's for work, whether it's just to socialize. And yet a very small minority of people know how to actually author it, how to write it. And so that's should be the motivating factor. It's like you use this all the time. You should know how it gets created. You should know how it gets authored. You should be literate in software, if for no other reason. If you're not going to go, if you decide not for it to be your career, you should at least know how the things you use on a daily basis actually works under the hood. So that's going to be my claim as a motivation for why we should pursue learning how to develop code, how to think algorithmically. But the other motivation is it's a lot of money and it's really nice work, right? You get the work environments for software developers are traditionally a very kind of laid back environment, and you get paid very well for what you're able to produce. And again, it's because there's not enough developers, and it's because it's a career that happened across one generation. You're looking at a domain that is still developing, which is what we talked about when we were looking at textbooks. Okay, so let's examine how writing and thinking in computer code is different than other forms of writing and thinking. So I'd wager to say, and again, one of the issues we have with why so few people know how to code is because the school systems aren't really set up for it yet, right? Like there's requirements for things like math and English and history, right? But how many people had required like software development or coding classes in your high school or in your elementary school? So I see one. How about online? How many people online? Yeah, I don't see. And so that's a deficiency. We're talking about something that you don't get trained on until you hit the university level. But now that you're here, you can take advantage of that. You can take advantage of that hole in the job market that requires that. But what I'm going to try to do is tap into those things that you do know how to do well. So you took math classes and you took English classes, right? So you learned how to develop concepts and ideas in a natural language. You learned how to do processing of operations in a formal language of mathematics. So what my role here over the course of the semester is to take those two skill sets you already have and adapt them into developing software. Those are going to be the two things we're going to initially rely on so that you can start thinking algorithmically. Okay, so with that said, let's start talking about how we even think about things. So I'm going to assume that everyone here speaks a natural language. If you don't speak a natural language, then I'm very impressed you were able to get into the university. So for all intents and purposes, natural languages are those that we can speak or we think or we can write in. So I, for instance, speak in English, but there's a huge number of natural languages that can be spoken. Let's look at how we use natural languages on a daily basis. So when you first learn to use a language, what you do first is you define a base set of characters. And you probably do this when you're like a baby, right? Toddler, you learn your ABCs. That's the set of characters, the set of values we have, at least in English, that we then use to combine together to form into words. So every word that we create is a composition of those characters, right? Everyone agrees with me on this, I would think, hopefully. Okay. But then what we do is those words have some kind of unique, interesting meaning, right? We ascribe to them, we bind to them, we have them represent some type of object or action or behavior or event, right? And so probably the first 12 or 15, or I don't know, however many years you go through class, you keep learning more and more words, right? Usually that's inside of some form of an English class. Am I remembering this correctly? It's been very many years since I've gone through the educational track, but I kind of remember having to memorize words and then give the definitions. And then we'd have like a quiz at the end. Like every Friday we have a quiz and they would give us a word and we'd have to give the definition. But what we're doing there is we're binding a representation, some mental concept that we have, and we're attaching it to that word. We're creating kind of a mapping. But then we learn how to combine the individual words together to make these more complex relationships. So we're defining relationships between the individual words that create an expression of sort, right? An expression that allows you to communicate some kind of information. Or you could either speak it, you can write it, or you can think it. Okay, that's natural languages. Let's talk about the properties of a natural language, though, some deficiencies, because the question is, if we're going to code, if we're going to do computer code, if we're going to build software, why can't we just use natural language to do that? Right? Wouldn't it be so easy? So everyone already speaks a natural language. Very few people in here already speak in like Java programming language. Why not use the natural language? That should be the first question, right? We have this thing that everyone uses. We want more people to author it. Why can't we do it like we would write a research paper? Well, and it has to do with some of the deficiencies of natural languages. So the entire point of a programming a computer is, well, when we look at the properties, I can't step away. It requires an intelligent speaker and intelligent listener for a natural language, right? Would everyone agree with that? So what I'm saying to you right now, you're listening to me, but you're not just listening to the words, you're then parsing the words in your mind. You're then you're attaching it to the mapping that you've been trained to do to be able to translate into the concepts, and then you build that relationship internally. So I've learned how to take the expression in my mind, encapsulate it in a form of data that you can then that you've learned how to parse and then reconstruct inside your own mind, right? When you effectively, is that a good definition of how we communicate using a natural language? Okay, so it's super important then that I'm intelligently constructing these sentences, but you're also intelligently reconstituting them. You're breaking them down and then formulating them into the mental model that I'm trying to have in my mind. So we can't use natural language to develop software because a computer is not intelligent. And despite all the awesome progress that you might have seen in the news about deep learning technologies, and it is super impressive. I don't know if you've seen some of the things that are out there. Has anyone seen like Midjourney or DALL-E 2? I mean, we're talking about these deep learning networks that you can give it a text prompt and it can generate a unique piece of artwork based off of your text prompt. It has the appearance to be incredibly intelligent. It has the appearance to have almost like a sense of consciousness, but it doesn't. It's just a really complex application. A computer has no ability to truly interpret the world around it. It's merely a tool, no different than a calculator or a ruler. Its meaning, what it does is no different than, its meaning is given to it by the implementer, the person who uses the tool. So all the cool stuff you see out there where it appears that the computer's able to process and do more than you is it's a facade, right? It's just a piece of application. And the moment that it doesn't know how to handle some kind of data input, it's going to crash. It can't, and so that brings me to the next thing I really want to highlight about natural languages, though. Natural languages, and this is both an advantage and a disadvantage, because it requires an intelligent perceiver and an intelligent speaker, it allows for ambiguity. So like I can be less precise, but you can still understand what I'm saying. I'll give you an example. I could say that that is a big wall. And so big is an abstraction. It's an abstract term. It's a relative term. Relative to what? I don't know. Like big isn't it's not a very precise term though, right? So because if I go ahead and ask each person, okay, I could do this with objects too. I can have everyone close their eyes and think of a cake. And so a cake in itself is not very well defined, right? It's not very concrete. It's an abstraction. And so when I say think of a cake and I ask, I'll probably get a different type of cake. And I can actually test this. Like, what kind of cake did you think of? A chocolate cake. And what kind of cake did you think of?
Actually, chocolate as well.
Oh, that's bound to happen. Rules of probability. What about you? A strawberry cake? Angel food. Look, so 4 people, 3 different cakes. And I love that. So sometimes you'll get the same cake, but sometimes you won't. So it's not a reliable measure to get repeatability, but it's an awesome measure just to communicate an idea or concept. So again, natural language is a great affordance to us to be able to communicate with as little information or as much information as we want at any given time. But because ambiguity is baked into our natural language, we can't rely on it as a programming language. Does that much make sense? Okay. So it lacks that precision, and what we need with the precision is the repeatability. So what we want when we develop software, and this isn't just in the world of computer science, what we want if we're physicists, what we want if we're biologists, what we want if we're chemists, is the ability to define, to describe the world around us in a way that it is repeatable, that it is precise, that when I write that down or I tell it to you, you implement it in the same way I did. And so that's where we can rely on formal languages. And that's where we can rely on things like mathematics, which is the science of measures. So a formal language are languages that offer the precision, which will give us the repeatability that we're looking for. And so here, I'd like to think that we're going to start learning how to speak in the language of math. That's going to make math a lot more fun and interesting to you all, because we're actually going to use it to do things with it. It's not just going to be rote memorization where I give you input and then you crank out output and you're like, I don't know why I'm doing this, except that I'm memorizing a process. It feels a lot of times when you're not applying it in real world problems, like it's a game that lacks fun, right? It's a set of rules and you're like, I guess I'm winning. I don't know. Okay, so in formal languages, we learn to use them in very much the same way we learn how to use natural languages. So how to say we did natural languages, we learned a set of characters. We can combine the characters together to create words, which we then ascribe meaning to those words, because in isolation, those words don't mean anything. And then you can combine those words together to represent these relationships between words or these complex expressions. Well, our formal languages of math does the same thing. It's just you were never tasked to ascribe representations or meanings to the character set, to the words that you were given. They were just entities. They were just characters for the most part, probably in most of, maybe not in all, but probably in most of your exposure. In fact, when I talk to a lot of incoming students, the math classes that they do find more interesting are the ones where you start mapping meaning to the values you're processing. Things like physics, where you're like, I'm using these functions to try to figure out a trajectory or gravity or something along those lines. Or it's things like geometry, because, I can see this circle and I can manipulate the area on it. And it's because now you're actually having real world cases where the numbers make sense, where they have a representational value of something, where it's actually expressing phenomena or observations around you. And so what we're going to learn how to do while programming is to do that all the time. In every confines, when we go to create a program, a piece of software, an application, we're going to be learning to use our different data types but numbers are an incredibly powerful format of it, but there are other data types we'll use as well. But we'll use a combination of all these different ways of quantifying our observations so that we can build up a language around it, a representation around it, and then relationships between those representations. So the same way we make our English sentences, we're going to start creating these mathematical models. And again, these mathematical models are used in every profession, right? So learning to do this, and again, this is a process you learn through this algorithmic thinking process that we're going to discuss in the first third of this semester. Learning to do this will aid you regardless of what your profession will be, whether it's an accountant or a business manager, or if you're an engineer, or if you go into the hard sciences, or if you go into the soft sciences. They all strive to build mathematical models because it's about precision and repeatability. When you publish a paper, and we'll talk more about this in the next slide. So in formal languages, we learn to define a base set of values, such as numbers, right? That's the equivalent of our characters. We can combine the numbers together to create or get new numbers that may represent, again, we can ascribe to those numbers a value that represents an object, an action, a behavior, or an event. And we can represent that using our definition of measures. That's the entire point of what math does, is we can, like, for instance, here, I have a ruler, right? This allows me to take something as abstract as space and convert it into the characters that we operate on in our formal language, right? Numbers. Okay. And then we can combine the representations together to form functions. That's what we call them in math. In computer science, we'll call them expressions that define the complex relationships between our individual numbers that have a representation in of themselves. All right. So can you start to see how I'm bridging the gap between how you maybe formally kind of understood mathematics and your natural language in which you use to craft stories or research papers or complete and complex thoughts? Okay. So let's talk about some of the properties of formal languages. So a formal language only requires an intelligent speaker, but the listener does not have to be intelligent. And what that means is you could have an intelligent listener. So if I craft it like a mathematical function, and if I gave it to you, you could process data in there. If I gave you the same values I got, you're going to get the same result, right? So if I said, say, for instance, I'm going to define a function x plus 4, I'm like, well, what if you put 3 into that? Well, my result and your result is going to be the same. It's not going to be like with the cake, right? I'm not going to get like 5 and 7 and 8 and 9, right? I'm going to get the same value. That's super critical when we go to build software. The fact that we get a repeatability to it, that the process is the same every time. Because why the motivating reason why we use software is because we're automating tasks. But you can only automate tasks if it's done the same way again and again and again and again. If it's done differently every time, then that's not science. Science is all about finding the repeatability in the world. If something constantly changes, there's no way to really describe it in a repeatable way. Okay, so it allows for precision, but what that also means is that I can give that same function, I think, what was it, like x plus 4, and defaults to the cake front portal. I can give the same function to something like a computer or a calculator, and it too can process the same result. And that's what we're looking for, that even non-intelligent entities can derive the same solutions, because that is what allows for our machines to start handling the work that traditionally took a person to do. Okay, so I'm also going to claim, even prior to this class, prior to going through the practice of learning how to express observations, express objects or ideas or concepts in a formal language, you probably already do that. You probably do it in very isolated instances, or maybe you already do it all the time. Maybe you are you're a physicist and you're just looking to take a class. But for those of you who aren't, I want to ask another question. How many of you have tried to cook before or made a cocktail before? Is there anyone who hasn't? Maybe that's online too. Is there anyone who hasn't either cooked? Sometimes counts, yeah. Okay, so let me ask you this. When you went to cook, how many used a recipe to cook versus just, throwing something together? How many of you did not use a recipe to cook? Okay. Now when I say recipe, let me get a little bit more precise. How many used written recipe versus a spoken recipe, like one that you got from a family member? Okay. So if you've cooked with at least one recipe, then you've essentially followed an algorithm. Recipes in cooking is an algorithm. And so you followed, or at least parsed, a formalized language for cooking. So think about the concepts that drive a recipe when you follow a recipe to make a cake. We talked about cakes earlier. There's a couple of different data types that we have to use to convert our real world objects into a system of measurable things. So why don't we think about them? So what are the ingredients I need if I'm going to make a cake? Like I need what? Like flour, I need eggs, I need sugar, I need milk, right? Okay, so let's first try to express the recipe for a cake using natural language. Because when you read a recipe, you might say, oh yeah, that's written in English. But I'm going to argue it's not in English. It's in a formal language designed for conveying recipes, for conveying instructions for cooking, for designing cooking algorithms. So a natural language would potentially have ambiguity. It could be like, oh, it's just like I said, these are the ingredients you need. You need some eggs, you need some sugar, you need some milk, you mix it together, right? You put that into a bowl, you mix it together, you put it into like a pan, you put it in the oven, you turn the oven on so it gets nice and hot, and then you let it cook probably for almost, more than seconds, more than minutes, probably less than an hour though, right? So less than an hour, and then when you pull it out and you have a cake, right? That's the general process. Would anyone disagree with that? Or do you think I mean, it's been a while since I cooked a cake, so maybe I got something wrong. Does that seem adequate though? But notice, if I gave you those as the directions and I told you make a cake with those directions, well, because of the ambiguity, right, that's not a repeatable recipe. So every cake probably from everyone here would be different. Sometimes it might not even be a cake or not a good one, right? So what do we do if we don't articulate our recipe in that way? So first of all, we need a way of measuring our ingredients, right? We just don't say, get some eggs and flour, right? We ascribe a numerical value. We use 2 eggs, right? And then how do we measure our flour? How do we get our flour? Because flour is like particulates, right? It's not, eggs are easy because they're discrete, right? Discrete means they're countable, right? That like 2 eggs are individual from one another. But how do I get a count for something like flour? Flour is like sandy, it's powdery, right? It's all together. I can't count each individual grain of flour. Like, do I put like 30,000 grains of flour into the cake? Does that seem like a reasonable? So what's our measure for flour? Exactly. So what we're starting to do is map a language, a formal language on top of how to measure ingredients for the purposes of cooking. And you've probably learned these measures, but not thought about this as a mathematical model. Tablespoons, teaspoons, ounces, pints, cups, gallons are all formalized models for us to be able to create repeatable processes in the realm of cooking, right? Okay, and so that talks about how we measure the ingredients. That's not the only model we use when we're doing cooking recipes, right? Let's extrapolate this further. Okay, so I have a measure. So we're going to go from me just saying, get some flour, get some eggs, right? To 2 eggs, a cup of flour, a cup of milk. I don't know, half a cup of sugar. I really don't know a real recipe, but I can make up one, right? I can make one that sounds reasonable just by ascribing it some actual quantities to these. Okay. So then the next thing I said is there's ways we can then process these ingredients. So just like with addition or subtraction or division, we can take numbers and process them into different numbers. We have processing operations inside of cooking. That's like mixing, that's like chopping, that's like in fact, there's lots of different terms for chopping, right? What are they? You have chopping, you have you can julienne something, that's a different type of chopping, right? You can mince it, that's a different type of chopping, right? What's that? Dicing, yeah, that's a different type. So we have all these operations that we could do to our ingredients that changes their state, that transform them in some meaningful way, that's going to be critical to convert our input ingredients into the result, the output we're looking for, which is a cake, right? Okay, so we know these operations, and we learn these operations the more we do cooking, right? Because these are very specific terms that have meaning, and you learn the meaning by engaging inside of the actions, by engaging inside the world of learning the recipe, the language, the programming language of cooking. Okay, so what are the other models that we rely on? Heat, right? We just don't say get something hot. There's an actual value we can ascribe to heat, right? What is that? Degrees, right? And there's actually multiple models for degrees you could use. We use one particular set of degrees here. But depending on what your methodology is, you might have to use, well, maybe not for cooking, you might use like Kelvin, you might use Fahrenheit, you might use Celsius, but these are all different measures for the same type of thing, right? To communicate the amount of heat. And then there's another thing. We don't just say, put it in for some time and then take it out. There's a model to ascribe the passage of time. What is that we use in cooking recipes? Minutes, hours, seconds, right? And so here, these are models that are so ingrained in our speech that we think of communicating these concepts as if it's a natural language, but it's actually a formal language that we embed within the natural language. So when we're talking, we can then refer to these models, these mathematical models, when I articulate something. And if I express my cooking algorithm, my instructions for cooking to you using these mathematical models formulated for cooking, the repeatability of getting the same cake is going to be quite high. Everyone's going to get a cake that's very similar if they follow the recipe, as opposed to the natural language recipe. That, again, is the reason why we want to use a formal language for developing our software. The same reason we have a natural inclination to do that, to describe any repeatable process that we want to communicate, even if it's something as simple as cooking a meal or mixing a cocktail. Okay, so let's formally define what an algorithm is, because this is one of the two things that we use to build software. An algorithm is an ordered set of instructions. That's all it is. So it's a sequence, right? And so typically it defines a sequence of states. So what I mean by state is the word state. Like sometimes I have to take a step back, because I've existed in the world of computer science so long, I use terms in a way that's meaningful to me, but it might not be meaningful to you. When I say state, does everyone kind of understand what that term means? I feel like that's a normal Englishy term, but yeah, okay. So yeah, so like the state of water can be frozen, it could be liquid, or it could be like steam, right? It can have, and I can change the state of water by applying heat or taking away heat from it, right? And so I could say, at this point of time, this is an ice cube. and then we can wait maybe 15 minutes, and then we get a pool of water, and then we can heat that water up, and then maybe 15 minutes later, it can now be steam or vapor, right? So when I mention state, that's what I'm referring to, that you can have some value. So here my value is the water, like what is the form of the water, it can change over time, right? Sometimes the state is constant, right? Like the state of this concrete wall is always going to be solid. Like now, 15 minutes from now, 30 minutes from now, but typically the things we care about when we design an algorithm is the things that can change state, not the things that are always constant, because that's where the magic happens. That's how we can get a cake. We can get an initial set of our ingredients, and we can keep changing the state of those ingredients until we magically convert it into a cake, right? Of course, it's not magical. We can see the evolution of the cake over time as we keep processing on those ingredients. Now, what we're going to do in computer science is very akin to what I just defined with cooking recipes, but we're going to generalize it. So it's going to be more than just being able to describe processes for making cakes. We'll be able to define processes for solving every problem that exists in any domain, because we're going to learn the craft of creating generalized recipes and generalized data models that we process a set of inputs into a desired set of outputs. And it doesn't matter what the output is, doesn't matter what the input is, and it doesn't matter what our processing terms are, we get to define those. So you can then create these recipes that solve engineering problems, or solve biology problems, or solve chemistry problems, or solve accounting problems, or solve management problems. So it defines a sequence of states, events, or actions that occur throughout a process from its starting state until its ending state. And again, think about the cake if you want to articulate that a little bit better. And so here, if I want to give you a little personal challenge, try to come up with your own algorithm, but instead of a cooking one, try to do it a little bit differently. Try to make a simple rule-based game. Now, I'm not going to spend any lecture time where we're actually going to do that, because that would be a waste of my valuable lecture time to you. I only get so many hours each week, and I have a lot of information I want to share with you. I have a lot of information that I want to share with you over the course of the semester. But I challenge you in your own time, see if you can create an algorithm and see how effective and efficient you are at least just using natural language or a form of pseudocode. So it's human readable. It's not designed to be an application or a software, but see if you can't define something that's step-by-step, that's so good that you can hand it to a friend or a family member, and they can follow it and play the game the way you intend it. Because that can show you some of the pitfalls that can exist with defining an algorithm, the step-by-step process, and using the appropriate data models to model what it is you're processing it on. Okay, do we have any questions from just this quick little intro? Is everyone with me? Does this stuff kind of make sense already? Good. And again, my strategy is to start at a base level, giving concepts everyone's comfortable with, and then we're going to keep adding complexity to that, so that by the end of the semester, you're primed and ready to go into the second software development class, where you can start learning how to code at a more professional level.